Everybody give a big warm round of applause to Monty Taylor. Looking at Monty's description on LinkedIn and on the website, I mean, there's various words that pop up. There's OpenStack, there's Rackspace, there's Red Hat, there's all sorts of awesome, amazing things. An originator of the OpenStack platform. Monty,
yes.
Welcome to Athens.
Thank you.
Have you been to Athens before? Was it your first time?
No, this is my first time.
First time in Athens? Give him a big warm welcome.
Yes. Thank you all for having me.
Fantastic.
It's showing you all of the things. That's not what you're supposed to see. Okay, there we go.
There you are. Okay.
That's much better.
I'll get off.
Yeah. So great. Thanks. Like I said, thanks for having me here. It's really fantastic. I'm going to chat with you a little bit about a piece of software called Zuul. But first, I'm going to talk about myself because I'm really conceited and I like to talk about myself, and that's how that goes. So I work at Red Hat. I work in the office of the CTO there, ostensibly working on CI and CD strategy. As if any of you have ever worked in an office of the CTO, you know that means that you write lots of documents that nobody ever reads. It's a lot of fun, but it's good. It's a good place. I came to Red Hat, as was mentioned, via my work on OpenStack. I've been working on OpenStack for 9 years now, which is a ridiculously long amount of time to work on one particular thing. Before that, I would usually do like 6 months at a company and then move to the next one. So I'm not really sure what I'm doing as far as that goes. My role in the OpenStack community has been building and shepherding the developer infrastructure systems, which is what I'm going to be talking with you about today, that help us develop OpenStack. So I don't really work on, it's hard enough to explain to my parents what we do in cloud software, but it's really hard to explain to my parents that I don't even work on the cloud software. I work on the tools that developers use to work on the cloud software. And at that point, they just try and hand me some more food. Anyway, so these are some nice things that some people have said about that. We've recently started, as I think Thierry mentioned this morning, working on rebranding our developer infrastructure tools as OpenDev because they're more potentially relevant to people outside of the OpenStack community, and we don't want people to think that it's only there for cloud stuff. As part of working on all of those developer tools, we wrote a piece of software called Zuul, which is mostly what I'm going to be chatting about today. For those of you familiar with the end of the movie, you can see in the logo there the gate that was behind Sigourney Weaver at the end of the film, and this is the ASCII art version of that. Yeah, so I'll talk much more about that. And it's actually a really great talk to follow. Zuul is very heavily Ansible oriented, and so I'm actually at Red Hat because of my friendship with the folks in the Ansible organization there, and it should hopefully become a little bit more obvious what the deal is with that. I suppose I should have said on the previous slide, in case anybody was expecting me to talk about the Netflix Edge gateway routing service called Zuul or the JavaScript testing framework called Zuul, that I apologize. I will not be talking about either one of those. I'll be talking about our project gating system called Zuul, because apparently Ghostbusters was popular sometime in the 80s. So in a nutshell, what Zuul is about is this idea we have of testing a speculative future state. Essentially, we don't want to test the code you wrote. We want to test the result of deploying the code that you wrote. Because while the code that you wrote might be wonderful, deploying it might be a terrible idea, and so we want to be able to shame you appropriately. One of the things that's really special about Zuul is that it handles the idea that your application might span multiple source code repositories. I don't know about y'all, but in my world, everything has been getting more and more complicated, and the idea that you're just going to stick everything into one source code repository, although I know it's what Google does, we don't necessarily have to copy all of Google's mistakes. We can think for ourselves sometimes and actually organize our code in the way that makes the most sense for us. But the idea that you have multiple repositories that go together into a single integrated deliverable, right? The thing that you care about is a larger portion that's made up of a bunch of smaller building blocks. And so we wrote Zuul to deal with that world. We wrote it to provide a concept that we called gated commits, which I will talk about in mind-numbingly boring detail in just a moment. Zuul is all open tooling. So it's really important to us, again, I think most of the things that I'm going to say will have some reference to something in a slide from Thierry this morning, but it's really important to us that we're able to do open tooling. So Zuul is there to make sure that we can do all of these things using completely free and open tools. In our community, we think that it's a really good idea for nobody to be special. That way everybody can be special. And finally, we think that you should test something like you deploy it. Just running some unit tests over in a corner is great. We do that. But we also like to actually deploy as production-ish a version of the software as is possible and test that. And we want that deployment to be as much like your actual production deployment as is humanly possible. Otherwise, you're testing that your test system works. And while that's great, and it keeps me in business, it's not really ultimately at the end of the day the thing you want to test if you want to test the result of applying your change into production. So before I talk in more detail about Zuul, I want to talk real quickly about OpenStack, because it was the original use case that we had was supporting the OpenStack developer ecosystem. And so there's some qualities about that feed into the design of Zuul that are important to understand. OpenStack it's federated, it's distributed. OpenStack the project, not OpenStack the software. OpenStack the software is also federated and distributed, but I'm talking about the people. So OpenStack the project is a federated and distributed, very large, open community that is not alone in the world. We're not on an island. We have a bunch of friends. What I mean by federated is that there's hundreds of involved companies, right? There's a ton of people. We don't have one main company. At the very, very beginning, there was one main company, which was Rackspace, but we have divested Rackspace's sort of primary role in the community, and they are now just one of many. So that means that decisions in our community are made by the people who show up to make them, whoever those people might be who show up to make them. And it means that we have to handle the union of everybody's priorities and use cases. There isn't just one company saying, nope, we're not going to do that, don't care about that. We have to serve all of the people that are members of our community. So there's some interesting things from a developer tooling perspective. Nobody can appoint anybody to positions in the project. Everybody has to earn positions of trust or control. The project can't fire anybody. If you're a terrible developer and you're just sort of disruptive, we can't fire you. It's the internet. You can still submit patches, which is great, I guess, in some ways. But sometimes it can be frustrating because sometimes, sometimes that would be easier than needing to actually work through and assume those sorts of things. We have a variable background. We have people from all walks of life, from all over the place, all sorts of different backgrounds. We've got to provide a home for all of them to work. Which means we've got a really heavy reliance on consensus. We do a lot of democracy. We do a lot of voting on stuff. We're very good at voting on things. We're better at voting on things than some people are these days on the planet. That's just, yeah. Anyway, so we're distributed. There is no office. You can't go to you can go to the office of the OpenStack Foundation, but there's 4 marketing people in there. It's not the office where OpenStack is written. Our contributor base is global. We are a 24/7 shop. There's always somebody pushing patches. There's always somebody reviewing code, which means also from a developer perspective, you can't assume that somebody's going to be in your time zone. We have a multitude of contributor backgrounds, as I mentioned. This means that our tooling has to empower all of our contributors, regardless of where they're from, right? Regardless of what their skill level is, regardless of whether they're a 16-year-old college student or somebody who's been in the industry like me for 70 years or something ridiculous like that. We have a heavy preference for text-based communication because I am absolutely amazed every time I go to a conference that is in a country where English is not the primary language, and I'm up here running my mouth in English, and all of you are like, yeah, no, of course, that's fine. Turns out there's lots of other languages out there, and it's important that we're able to communicate, even though obviously that does wind up being in English. But I can talk really fast, and not necessarily everybody across the planet can keep up with this voice right here. But on the typing, it gives people a little bit more of a time to process, think, and be like, oh, that's what he was saying. That doesn't make any sense. And then they can pick on me for that. From a tooling perspective, we can't assume US-centric needs or solutions. There's a lot of folks in sort of the Silicon Valley background who just assume everybody lives in San Francisco. And I guess from their point of view, probably everybody does live in San Francisco, but we believe that there's people that live in places that aren't San Francisco. And ultimately, our tooling has to be able to handle accepting patches from people we don't know, on the internet that we've never met before, and treat those that way because that's kind of what happens. We have large numbers of all of these things. In any given 6-month period, we have in the 2,000 contributor, 2,000 discrete contributor size thing. We have tons of changes that all of those lovely, lovely contributors write for us. And as I counted this morning, and we have 2,082 source code repositories. There's marketing people who really like to brag about numbers and like compare each other and whatnot. This is, as a person providing tooling for this community, this is my incoming use case, and it keeps me up at night because this is 2,000 contributors worth of chaos that comes directly at my systems and whatnot. So this is not me bragging about scale, and the next slide is certainly not me bragging about scale, but Thierry already did some of these numbers, so it's okay. I'm not the only one. So we do about 2,000 jobs an hour in our system, and as I'll mention later, each of those 2,000 jobs creates at least one and sometimes more than one cloud VM, so we are very good at consuming cloud resources via API. Our build nodes in our system span 16 regions of 5 public and 3 private OpenStack clouds. So not only are we running the tools that people are using to build OpenStack, we are consuming OpenStack clouds for the build resources that our OpenStack developers are using to build OpenStack, which is kind of really cool. And then in fact, for each of those patches, we're deploying OpenStack on those VMs that we're getting from OpenStack clouds. So it's a fun day in my life most days. These are the lovely people who give us those things. And we merge, give or take, about 10,000 changes a month. That's after fully integration testing all of those changes. Just as by way of comparison, I love our friends at Ansible. It's a fantastic project, and I use it every day. In the first 4 years of their project, they received 13,000 changes and merged 8,000 of them. That's not to compare ourselves to them. We do different things, but to give you sort of an idea of what I'm talking about when I say 10,000 changes a month, because that's kind of a number out of the clear blue and is sort of potentially meaningless. So yeah, we have fun. It's a lot of fun. Thierry mentioned these earlier, so I won't spend a lot of time on these. We hold to the 4 opens, so open source, open design, open development, open community. In our tooling world, we actually we have a 5th open, I think, which is open operations. So all of the operations of all of these tools is all done in the open, and it's all done by landing commits into source code repositories that themselves go through testing. So we're sort of hyper believers in all of this open. All this open stuff, which is a lot of fun. I said earlier we're not alone. We have 2,082 source code repositories in our systems, but we also are heavily dependent on other ecosystems. And it spans from things like libvirt kvm zen to MySQL Postgres, Rabbit, those types of things. We have adjacent communities, Ansible, Kubernetes, Terraform, any of these things. And then there's all sorts of vendors. I don't know if any of y'all are aware that there's vendors out there who like to sell products based on open source software, but they're a vibrant part of our ecosystem as well. We have drivers for their hardware and all sorts of different plugins that are important for the vendors, and we've got to sort of interact with this wider ecosystem as we do all of our stuff. So our world is in a large part not just about the interdependencies of OpenStack, but the wider set of dependencies. We're not sort of in a vacuum. It'd be really nice if we could kind of computer science course just I've got my perfect little bundle of isolation here, but the real world doesn't really work like that, and it certainly doesn't for us. The primary purpose of all the tooling that I work on is to serve our developers. So the next thing is to walk you through, and this won't be news to most of you, I imagine, because this has sort of become the way lots of people do things, which is great. This was not necessarily the case 9 years ago, but we require everything to go through code review. If you're from a GitHub background, that means sending in GitHub pull requests. In our case, we use a tool called Garrett. But one of the things that we did early on, and by early on I mean from the very first commit of the project, is we took away everybody's commit access. No one in the project has commit or push access to the project. All commits are always landed through automated testing. And the commits will only land in the repositories if they pass the tests. And it has always been that way since day one, which is a lot of fun. We have a system of third-party CI for vendors. Turns out if you're HPE and you have 3-par SANs and you would like to have drivers for OpenStack's block storage product Cinder, or block storage project called Cinder, and you would like to test those, I can't possibly test those because you're not going to give me hundreds of thousands of 3-par SANs. And even if you did give them to me, I would have nowhere to put them because all of my resources are being consumed in the public cloud. So we rely on a system where vendors are empowered to test their driver plugins that they care about. And if they report back that their plugins work great and they're lying, the only people that this is really hurting is them because it's their customers who are going to be really angry when that driver doesn't work. So we try and empower them to do that, but we can't possibly do all of the things centrally. And we try and distribute as much of that as possible. So this idea that we have everything run through code review is the idea that we refer to as gated commits, which I will talk about in more detail in a second. This is for those of you who prefer graphical diagrams of developer process. This is basically what it looks like. A developer clickety-clicketies in their editor of choice. They push code up via Git to our code review server, Garrett. And then they sort of do that in a loop. I've typically got hundreds of patches out at one given point in time because I write terrible code and people take weeks to tell me what all is wrong with it. So I do lots of things in parallel. So you sort of do that. It's up in the code review system. People are reviewing it. Once people approve the code that I'm wanting to do, it goes through our gating system, Zuul, and if the tests pass, it merges, at which point I can clone it and pull it down and add new patches on top of it. That means that for us, the code review system is actually the primary user interface for Zuul. It's a little bit weird. We have a web dashboard, but that's like for reporting and sort of checking up on things later. We want the developer's primary interface with the system to be in the place that they're already interacting with, writing code, pushing things up into code review. So we leave comments and we leave statuses in the code review status. This is also a thing that GitHub finally caught up with, which is very exciting for them. But it's a really useful thing to be able to have the developer not have, here's where I'm coding, and then over here there's this build system I'm paying attention to all day. No, pay attention to the code. Stay in your code world, and we'll get the data to you there in the place where it's the most relevant to what you're doing. As may have figured out, Zuul is not a new piece of software, although we've been doing a bunch more marketing about it recently. We've been running it in production for the OpenStack project for about 6 years. Our most recent major release was called Zuul v3, and it was the first release where we had decided to accept people who weren't OpenStack as first-class use cases. We had people using the previous versions of Zuul, but we weren't designing it for them, and it was hard. They would complain. They were like, wow, your documentation is not particularly very good for me to install one of these. We're like, well, that's because, I mean, it's open source, but we didn't really write it for you. We just wrote it for OpenStack, and it's a happenstance that you can run it. And we finally realized that that was really mean, and we should pay attention to people that weren't just ourselves, even though that doesn't feed my narcissism very well. So it's out there for everybody. We are also an official official pilot project of the OpenStack Foundation at the moment, and hopefully we will be one of the first confirmed new top-level projects of the foundation in the next few months. I hope, fingers crossed, unless people hate me, which is a distinct possibility because I yell at people. So it could just not work out. But we've been doing it for a while. So it's both new and old all at the same time. I mentioned it's not just for OpenStack. It's already in production at many places that aren't OpenStack. The fine folks at BMW are running a very large Zuul that is testing self-driving cars, which is terrifying to me because like working on cloud software is one thing, but like I could introduce a bug into the testing system that causes somebody's self-driving car to crash something, I think. I don't know about that. I'm a little bit more comfortable about GoDaddy running it for websites. That's okay. There's a fintech startup called Good Money that's doing one, Le Bon Coin, big e-commerce out of France, a whole bunch of other people. We keep discovering people running it, which is kind of, I think, one of those crazy open source things where you're like, well, I mean, we can change this. Nobody's going to be using that feature. Oh, no, there's lots of users that we didn't know about. So that's a bunch of fun. The best way that you learn that a feature was actually in heavy use is when people complain when you remove it. So in a nutshell, what Zuul does is it listens for code events, listens for events from the code review system. It prepares appropriate job config and Git repo states, which I'll talk about next. It then allocates the needed nodes that you need to run your test jobs, because you have to be able to run the test job content somewhere. Gets the Git repository state to the nodes, runs whatever Ansible you tell it to run, collects and reports the results to you, and potentially merges the changes. It's really simple, right? That's all it does. Piece of cake. Nothing to see here. Whatever. The devil is in the details a little bit in that. But this is all in the service of this thing I mentioned earlier, which is gating. And so I want to take a couple steps to sort of get to what gating is and sort of how we got to the idea of gating many years ago. So in the beginning, there's the wonderful world of developing with no tests. It's okay, we all do it. This slideshow has no tests. There are things where it doesn't make any sense to have automated testing for the development you're doing, and that's okay. It doesn't scale very well from a developer perspective. Once you get past one developer, it's really a terrible idea to have completely no tests for your. It's really a bad idea to have no tests for your software, generally speaking. But like you can get away with it if it's just you, like for your automation for your home with your lights coming on and off. Probably running that through unit tests is a little bit silly. But it's okay. Or you'll have manually running tests. You've got some, but you run them whenever you feel like it, and you check it. And this is okay, but it doesn't really scale organizationally. People then really started picking up on this idea of periodic testing. Right? This is actually the original use case that Jenkins was written to solve. Right? It's running on a server beneath Kosuke's desk at Sun, and just periodically running the build for the team. And that was a giant light bulb for tons of people. Wow, we can run nightly builds. This is fantastic, and report things that still work. This leads to a lot of patterns like people tracking down who broke the build, because in a given day you probably landed more than one commit in the thing, and so when it breaks, you're like, well, crap. One of those 100 changes that we landed in the last day broke, and so you've got to do all sorts of forensics or blame tools or things of that nature. It's a very reactive. It's a very reactive system. A little bit still reactive, but a little bit quicker on the game is post-merge testing. I have landed a change in the Git repository. Now I'd like to run tests to make sure that the Git repository is still working. This is better than just running them nightly, but you're still in sort of reactive mode. And a lot of times, due to resource constraints, people will roll or batch things up, right? So you're still doing 5-10 patches at a time, because nobody really likes to spend money on test resources for organizations. It's always the last thing anybody wants to fund. So you're like, well, I've got that one machine over there that we use to develop a cloud operating system. We don't want to throw too many things at it at once. So you do that. It is easier to diagnose which change broke things because you're running on a smaller set of them, so that's still better, but it's still reactive. Pre-review testing is, I think, all the rage these days. Pretty much everybody is doing this now, or at least most people are doing this. This is where you're testing your pull requests. You're testing your code reviews, right? You push your changes to a code review system like Gerrit or GitHub. The CI system is triggered by the creation of that change, and the CI system then tests that change. And that's awesome, because that gives feedback to the developers reviewing the code as to say whether the code works at all. Because reviewing is a really human-intensive task that takes a lot of energy, and you don't want reviewers spending all that time reviewing code that a computer could have told them doesn't compile. Get the code working at a basic level first, and then you can have the reviewers focus on things like, is this patch a good idea? Right? Does this fit into the overall direction of the project? Not, or do you have the syntax right on line 5? Right? A computer can tell you that. You don't need a human to be the person doing that type of code review. It's not useful. Reviewers can get really bored waiting for tests. You see this a lot. They're like, it's going to take another 30 minutes for those tests to finish running, and I'm pretty sure this one is fine. I'm just going to merge it. It's no big deal. Everything is going to work just fine. And the thing that's sort of a hidden hidden problem here is that this only tests the code as it was written. It doesn't test the result of landing the code if you've got people working in parallel, because it can only test it in the context that it exists in. But if you've got 4 things sort of going at the same time, they could conceptually conflict with each other. And the testing that you did on the state of the patch as it was written is invalid testing, because you're not testing the result of merging it, which is where we got to the idea of gating, which is, again, like the post-merge testing, changes are pushed to a code review system. The gating system is triggered not by the creation of the patch, but by the code review approval. Somebody says, yes, merge this patch. Then we start running tests. And we run those tests, and we automatically merge the code if and only if the tests pass for that change. It's proactive. You're testing it before it lands, so the build is never broken, right? Like you have a always working baseline for everybody to work from, and you're able to test correctly the future state resulting from the merge of the code, which means that your reviewers can fire and forget. This is a thing Jess Frizzell last year tweeted out. She's like, hey, GitHub, could I have a merge this if the tests pass button? I was like, yes, Jess, you can have that. I'd like to introduce you to my friend Zuul. But it's a thing that's really useful because it means developers don't have to context switch and like worry about it. I want to land this, but I don't know if it's gonna, I've got to wait for the test, and now I've got to come back later and trying to remember what my context was, and people can actually just focus on their job and let the computers handle the hard combination things. These are not mutually exclusive forms. We actually use, well, we don't use the no tests version, but in OpenStack land, we use all of the rest of them that aren't no tests at different points in time. So we actually test patches as they're written when you create the review to feed into the review process so people know whether to review the code or not. We test it again after you approve it to get that second correct testing in there. We run things after changes have merged for things like documentation publication. We run things when somebody pushes a tag to do releases, things of that nature. So a full system will be able to do all of these things. It's not that one is necessarily better than the other, and they all feed each other and whatnot, which is really good. We even have periodic tests that we run because it turns out operating system dependencies shift. Even in stable releases of operating systems, sometimes IP tables can get broken, magically out from underneath you. And you need to know about those sorts of things rather than just waiting for the next patch that you push. So in our world, as I mentioned earlier, multiple repositories are required for the deliverable that we're shipping. It's not just a library. It's not just a desktop application. It's a whole fleet of services that all interrelate. So for us, when we test the future state that we need to test is the future state of the collection of projects that go into the deliverable, with all of the repos involved. And so to do that correctly, you need to get the tip of each of the projects. You need to merge all of the appropriate changes that are in flight in your queue, and to get it correct, you have to serialize those changes. Otherwise, you're not able to predict what is the future state that I want to test so that I can see if it works. Otherwise, you're just testing random states that won't ever exist in the real world. So you need to put those things that share an integrated deliverable into a shared serial queue. Obviously, if we have 2,000 developers pushing and we're trying to land 10,000 changes a month, we couldn't actually put these we couldn't actually do all of this serially, because then we would land maybe 10 patches a day. It would devolve very quickly. So this is where we brought in the idea of speculative execution from processor design, right? Like optimistic branch prediction. So we create a serial queue of the future states, assuming that all of the things ahead of any given change in the queue are going to pass, because they have gone through testing once before and code review. They should pass, right? So we assume that's going to be the case, and then we parallelize the testing and execution of that virtual serial queue of changes. And then if something fails, this has been dubbed the Jim Blair algorithm, if change fails, we move it aside so that we can later on report it back to the user, cancel all of the things behind it in the queue because they couldn't possibly succeed, because we have a captive gating system, so if there's a failure, none of them are going to be able to survive. But their subsequent failures could be because of the failing change. We move it to the side, reparent all of the changes behind it in the virtual serial queue, and restart all of those jobs in parallel. with the new state. And as I'm sure you can imagine, doing this by hand as a human would drive somebody completely insane. They would quit their job and probably quit tech and just go out and farm goats. Because, I mean, yeesh. So if following those words didn't necessarily make immediate sense to you, and that's fair, it's a lot of words, and a lot of words that are maybe not normal. I've got a little animation for those of you who enjoy ASCII art animations. So this assumes a world where the things are wonderfully simple. There are only two projects. They are called Nova and Keystone for absolutely no reason. Any resemblance to the real world is only incidental. And those wonderful 7-character Git SHAs are the state of the current tip of their Git repositories. So what happens in our simulated world here, the way this works and what Zuul's going to be doing, is a human at some point approves a proposed change to Nova. And so Zuul notices that, says, hey, somebody's approved a change to Nova. I'm going to start running some tests on that. And so it takes the current state of Nova and the current state of Keystone plus that change, sticks them onto the test nodes, and starts running some tests. Another person that is completely unrelated to the first person approves a change to the Keystone project. But because these share an integrated output, we need to test these things together, right? So for this test, we get the current state of Nova plus the current state of Keystone plus that Nova change number 1 plus this approved change to Keystone, and we put them on some test nodes and we start running tests on them. Somebody approves a change to Nova that is completely unrelated to Nova change number 1 or Keystone change number 2. So as you might imagine, we get the current tip of Nova and the current tip of Keystone and the Nova change number 1 and Nova change number 3 and Keystone change number 2, and we put them onto the test nodes and we start running tests on them. And you probably get the pattern and where this is going at this point. Another completely unrelated change happens. Nova number 1, Nova number 3, number 4, Keystone number 2, put them on the test nodes and we start running tests. And thankfully it is a computer doing that, because again, I'd be farming goats if this was my job. So then what happens is we notice that one of the Keystone tests fails. Oh no, that's terrible. Everything we're all gonna die. Well, we're probably not, it's an identity service, but still, it's important. We don't wanna do anything with that. We don't know yet, because the tests are still running for that Nova change number 1 ahead of it in the queue. We don't know the cause of this failure yet. It could still be caused by Nova number 1. What we do know for absolute certain is that Nova change number 3 and Nova change number 4 in this testing configuration cannot land. So we cancel all their tests, release their test nodes back to the cloud. Those test jobs are useless. This, incidentally, is the thing that we did that got BMW to start using us originally. They're like, we have all these tests that are running that are no longer valid, and we would like to stop using the nodes that they're on and cancel those things automatically, which was a feature that we didn't have even documented. I have no idea how they found it. They're just really smart. So that's how we got them. So we cancel these. We move this Keystone change sort of over to the side, because if it turns out this is a failure in this change, we want to tell the developer about it. So we don't want to just cancel its jobs. They're important. But we don't know anything about them yet. And we reparent Nova change number 3 on the nearest non-failing change in the virtual serial queue. So Nova, now the state for this is tip of Nova plus tip of Keystone plus Nova number 1 plus Nova number 3. And then the same thing for Nova number 4, right? The Keystone change number 2 is out of the equation. As we're doing this, all of the tests for the first Nova change pass. Yay! And so we say, OK, you're at the top of the queue. Nothing else could change your state. You're valid. And we're going to merge you. Automatically, boom, you're merged. Now, there's this failure in Keystone's tests. We know that that's a failure in the Keystone patch, or we can be pretty assured that it's either a failure in that patch or it's some sort of logical intersection that happened between these two patches. So even they don't share a Git relationship, they share a systemic relationship. So maybe something in that Nova change did something that is incompatible with the Keystone change. It's probably just a bad Keystone change. But we don't know that. But we do know that we can report this back to the developer and not merge it. And somebody can go fix the problem before it lands and messes everybody up. And in this case, Nova number 3 succeeds, so we get to merge it. And Nova number 4 succeeds, and we get to merge it. And all of that got to happen just by 4 people hitting the approve button at random points in time. But we're able to do all of that as correctly as humanly possible, thanks to the magical power of elastic cloud computing resources, which thankfully in my world are free. So, which is my favorite part about them. And sorry, Keystone, for picking on you in there. So that is cross-project dependencies that are happenstance, right? They come from just the random ordering of events of random developers randomly approving random patches in time, and the fact that those happen to share a relationship. Sometimes you're working on a project, or sometimes you're working on landing a feature where you need to proactively express a dependency just to chat with each other as part of the collaboration process, right? We've got people working on hundreds of different projects. They still all need to talk to each other. Like this isn't an excuse for them to be isolated in the silos and never talk. So we give them some tools to do this, which are explicit cross-project dependencies. A developer can put a depends on footer in either their commit message if it's a Garrett system, or if they're using GitHub, they can put it in the pull request description, saying this change depends on a different change. Zuul will use that, take it into account when it's creating its testing matrices, and it will not merge changes in a gating relationship if a dependent change has not landed. So it will also is a way for you to say, don't land this until this other one lands. It's incidentally also a way, if you're using Zuul and GitHub together, a way to actually do stacked patch series, which you can't otherwise do with the pull request model because it rolls up dependent changes into the first pull request to make them hard to review. But anyway, so that's a cool happenstance. This works both with cross repositories and cross sources. So we've done patches where it's like this change to Zuul depends on a pull request in GitHub to Ansible. And it will know how to pull those Git repository states and make sure that we can test Zuul in the context of a bug fix or a feature request that we're sending upstream to our Ansible friends. As a specific example of that, and I apologize, I don't have another great ASCII art animation. Jim made the other one, and I'm not good enough at ASCII art, so I need to cajole him with these for me for this. This is actually one that I've been helping some people with recently in OpenStack land. There's a service called Nova. It talks to a service called Ironic for bare metal resources, and it's currently using a library called Python Ironic Client to talk to Ironic. We want to get rid of Python Ironic Client because lots of reasons that I won't bore you with right now. We want to replace it with the OpenStack SDK. So somebody starts working on a patch for that. They need some plumbing. They make another patch, and they realize that as part of doing that, they need to make some improvements to the OpenStack SDK because it's not quite good enough yet to do what they need to do. So they write a patch to OpenStack SDK, and they label their Nova change to consume it as depending on this change. Because what we're doing is we're plumbing in some new config reading capabilities into the OpenStack SDK library, right? So we'd like to make sure that they work and they solve Nova's use case before we land them and release the library, thus committing ourselves to maintaining those interfaces until the end of time. So we'd like to get this right. So we put up the Nova plumbing change. We add a dependency on the dependent library change. And then it turns out, just to make it even more fun, the OpenStack SDK depends on another library, and we need to make a change in that library too. This is one of these really fun, you're like, oh, well, the right way to do that is to fix this all the way down the stack in this sort of HTTP transport library that we use. So we do that, we push it down, we make another depends on, so now you've got a stack of a Nova change that depends on an SDK change that depends on a Keystone Auth change. And the main thing is we want to be able to test these as part of the development process as if the library changes are going to land so that we can show in the Nova tests this is going to work for Nova. It is worth people's time to review the changes. It helps to explain the feature request to the libraries. They go, oh, okay, no, I understand why you need to add that feature in this library and why you don't just do it in your application. And we can see the end-to-end. Then we can land the changes in the libraries once we're confident that that is a good idea. So in the gate, it's very similar to the animation I showed you. When Git prepares the Git repositories for the final sort of Nova ironic change, it's going to get a tip of Nova plus the two Nova changes plus OpenStack SDK Git repository, its config helper change, the Keystone Auth repository, its helper method change. And this is how it's going to test everything even before it gets to the gate stage, because we've told it this is a stack of related patches. So it's going to do that, and it's not going to let us land those Nova changes, which wouldn't work, until we land and release the code, which is a really cool thing. And we thought when we added this feature it was going to be one of these like things that people use once every 6 months, and it turns out to be an extremely powerful developer tool that people use constantly because it's a way of actively communicating intent and verifying that that intent is actually a valid thing before committing people to long-term support relationships, or backing people into the position where they're always like, well, I really want to bump the major version because we need to clean up this cruft that we landed in the library that's crap, and they're like, well, now you're just messing up with your API boundaries for your own cleanliness. So anyway, I'm a really big fan of that. One of the things we don't support with this is the idea of a lockstep or circular change, and that's because OpenStack has come from a world of continuously delivered distributed services, and if you required a change to Nova and Ironic to both be deployed simultaneously across your entire infrastructure, that would be really a hardship on the deployers who are trying to run CD from master. So we've explicitly not added that to Zuul thus far. However, as we've been picking up all these non-OpenStack users, we've got a bunch of people who've actually got some valid use cases for that, specifically people working on things like desktop applications, where it may be in 4 different repositories, but you're delivering that one executable at the end of the day, and doing a dance of like, I'm going to add a thing here and remove a thing here, and then a 4th patch to remove the thing. It doesn't make any sense for them, because that's not how their applications. So we're going to add that feature, but we're going to make it possible for an administrator of Zuul to disable it, so that people who are focused on continuously delivered services can avoid breaking themselves unwittingly. And I'm to the point where I'm going to start talking even faster than I already talk because the screen is showing me the red color, which means that I'm a bad person and I have too much content, which is always true. Zuul is there to manage Git repositories. So the basic piece of configuration you give it is, here's a list of the Git repositories that I want you to manage. And then what it does when you start it up is it reads that config file with that list of Git repositories. It asks its fleet of Git merges. Git merging is a computationally intensive operation, and it turns out that you can't handle it just all on one machine. So we have a fleet of machines whose only job in life is to perform Git merges. So we ask the fleet of Git mergers for the branches of all of the repos of all of the things in the Zuul config file. Then we ask it for any Zuul config files in every branch of every repo. And we construct the change from that. As people are working, if they push up a change that changes the Zuul config for that repo, we notice when Zuul sees the change, because Zuul is there to manage landing Git repository changes, right? Zuul asks mergers for the updated content, and it splices any of that updated content into the live configuration that's used to test the change that contains the change with the change to the testing configuration, right? So this means that you can make changes that depend on changes to the job definition that tests the project in question, which means that you can write self-testing test job tests, which is really great, because I don't know if any of you have been in that situation where like, I want to update the test job people are using, and I'm really terrified that that's going to break 1,000 developers, and people are going to be mad at me. That's really the main reason we wrote that. But it's a really cool thing. I think these days I'm supposed to say that Zuul is a microservices architecture. I used to say that Zuul was a distributed architecture. I'm sure next year I'll say it's a serverless architecture. I'm not really sure what the fun word for that will be, but it's a distributed application that has lots of pieces that talk to each other over the network. We have to run job content somewhere, and I mentioned this in passing earlier. There is a separate but closely related piece of software called Nodepool. That's sort of part of the overall Zuul project that is required for Zuul. Zuul must have Nodepool. You can use Nodepool without Zuul. And its job is to create or destroy cloud resources for you to use for your testing of your nodes. Those resources can be VMs from an IaaS cloud. They can be containers. They can be entire container orchestration engine context, such as a Kubernetes namespace. Or they can be bare metal machines. They can be pre-existing nodes. If you've got that one machine that's connected to the really expensive HP SAN that you want to use to test your volume driver, you can check that out, test it, and do that. It also optionally will build base images for you to use and upload them to clouds for you. We currently support OpenStack, static predefined nodes, Kubernetes pods, Kubernetes namespaces, and AWS as places to get test nodes from, and we have people working on Azure and GCE support for where you get your test nodes. And this is where also I'm really thrilled about the talk that came before me. All the job content is written in Ansible. Doesn't matter if you're using Ansible or not in your world, you will be using Ansible if you do Zuul, because it's excellent at running one or more tasks in one or more places. It's really, as we were writing job description languages, we're like, wow, that looks really a lot like an Ansible playbook. We should just use Ansible. So the answer to most people's questions of how do I do this task in Zuul is almost always, Zuul doesn't know anything about that. You write some Ansible and it does the thing, because Zuul's job is to get repository states in the right, get repositories in the right state and then run Ansible playbooks on them. So we have jobs. They, I've got like a minute and a half, I think. They define node types needed from node pool. They define which Ansible playbooks to run. One of the other really cool things about Zuul, I showed you it'll grab the Zuul config from the repos under test, but you can also have centrally managed job definitions, which allows you to collaborate between a central testing team that maybe is focused on things like everybody needs to run this compliance test, and you as an individual developer don't get to decide whether or not you run the compliance test. But in general, we'd like for you as a developer to have as much freedom and flexibility as you need to do your job. So we hope that it diffuses some of the tension between those competing needs. You can have inheritance in the jobs, whatever. So anyway, I think I'm 4.5 minutes over, but these are some important links. The second link in there is where the source code is right now. In 2 weeks, that will be a different URL because we're rolling out OpenDev, so it'll be opendev.org/Zuul. This will redirect to that, so it's still a safe link. But just to send, there's some docs. We hang out on IRC in the Zuul channel on Freenode. And there's some also documentation for some of the OpenStack's Zuul jobs. And at this point, are there any questions, or is it time for me to run away because I'm over time and people are mad at me?
There's always time for good questions.
Oh, good.
Always time for good questions. Here we are. There's the first one.
How can you be sure that tests are always correct and does not drop good code? That is an excellent question, and it brings up a very important point, which is that what Zuul can do is it can run the tests that you tell it to run, and it can run them correctly. If the tests are crap, it's going to happily, very correctly run the crap tests. So that is a task for humans. As a specific strategy, one of the things that a lot of us try and do is we'll write sort of multiple different types. So I'll have some unit tests that mock out HTTP interactions, and then some functional tests that actually spin up a service and talk to it. And those are sort of two different implementations of the same thing, and they should check out with each other. And if the live one against the live service works and the mock test doesn't work, then the mock test is bad, and vice versa. But that is still a human engineering problem, and it's where we want the human engineering to go, which is humans making decisions about whether things are good or not. Does landing a change require test coverage? No, that is a social thing. Landing a change, to be able to land a change, Zuul must know at least one test job to run against that repo for that change. We have a built-in test job called no-op that does nothing. So you can use Zuul to auto-merge your patches for you with absolutely no testing. So again, this is a place where the humans have to decide what is the appropriate type of testing. We've had people request things like, hey, can we make a test that ensures that code coverage doesn't go down with every commit, or that every commit has a test coming along with it? And that gets really squirrely when you have things like people refactoring documentation or whatnot. And so from a systemic perspective, we've handled that as a code review policy rather than a technical gating, physical gating thing.
Let's throw a few more questions to Monty, because we have time, and we're not going to, it's rare that we'll have Monty here in Athens and on the stage, right? I mean, I'm sure we'll get to him later on with some coffee or a beer or something like that. But
come in anytime, coffee and beer.
Use the time now. There we go. Can we get a microphone to our friend here in the front row?
The biggest competitive advantage of Zuul compared to Jenkins or GitLab CI?
So in general, sorry, I will repeat the question just in case people didn't get it. What's the sort of benefits of Zuul over things like Jenkins or GitLab CI? There's a couple things, and some of this I think comes to intent and what you want to do with something. I love the Jenkins and the GitLab folks. They're all wonderful folks and they have wonderful tools. Zuul's focus is on gating. That's the thing that it does. And it focuses on being able to do gating correctly, both for single repositories and collections of multiple repositories. And that's sort of its unique thing that it does. It's also very focused on having your content be written in an otherwise reusable language. This is the reason why we focus on Ansible. Your Ansible playbooks that you're using to deploy your service to test them should be the same ones that you're using for production. So we don't really have a test-specific DSL that you can write Turing-complete code in to describe your tests, because that's very test-specific. So that's some philosophical things from our point of view. One of the other ones is it's designed to be a service. So one Zuul should be able to, like, if I don't know, if Nokia decided to go all in on Zuul, they should be able to deploy one Zuul for all of Nokia. And have all of their developers use that as a service, rather than having every team of 10 engineers have a half of an engineer's time be spent managing the Jenkins deployment, right? So it's focused on those sorts of bigger development in the large kind of problems. But if the other things are working for people, you should absolutely use them. They're wonderful tools. If two tests in two different repos succeed while isolated, they get accepted, but they finally cannot integrate together. Yes, that is exactly the problem that Zuul's speculative execution is designed to prevent, because we're going to be testing them in combination with each other when they go in. So that's why we do that whole kind of crazy thing. Does Zuul assume that any changes in its dependencies will always work correctly? This is actually really important. This gets back to human things. We can only control the things that we can control. So if you look at OpenStack, there's the sort of local tight dependencies. We know that we are collectively developing Nova and Ironic together. Or in Zuul, we develop Zuul and Nodepool next to each other, right? So we can ensure that. But if Garrett or Rabbit or Zookeeper or something like that outside of our control goes sideways, we can either have managed that in our own source code by having pinned dependencies. So we work with Rabbit 3.5.7 or whatever like that, and we always are pulling that in. Or we can, depending on what we're doing, sometimes we actually explicitly don't pin because we want tests to start failing when the ecosystem changes around us. A really good example of this was last year. A stable release of CentOS changed the semantics of IP tables such that it broke some patches for people in the OpenStack CI system. But that's really important to know, because that's a breakage that's going to happen in the real world to real users. So you don't want to protect yourself in the development environment from that change, because you need to fix your code to deal with, because you don't get to roll back that stable release of CentOS, right? You have to fix it. Sometimes that's just life. So it's really sort of depends on the interaction, who it is, and you've got to make some human judgment calls there as well. Then is there automatic utility in Zuul to find dependencies? No. But there have been people that have written some scripts, and some people have talked about that thing. In general, we go for the Zuul config is some reasonably simple YAML, so just splatting out a little bit more YAML is not particularly hard. We do a lot of magic, and we want to keep that magic confined to places where it's okay if people don't necessarily understand everything it's going to do, because it's going to do it automatically for them. But sometimes automatic dependencies, we're a little bit worried that might get too automatic and people would not be able to debug it. Anyway. What is the output of failed Zuul run? Yes. So can it be configured to fetch extra output from running gate tests? One of the really cool things that we do in OpenStack land, so when we're testing OpenStack, we are spinning up one or more machines, installing an entire cloud operating system, And oh no, I got okay. And then like I'm done talking. We're installing that entire cloud operating system on it, and then testing it by doing operations in the cloud. So just the test logs from the test run are not going to be sufficient for a developer to be able to debug what might have gone wrong with something. So we collect from those tests all of the system logs of the systems. We collect all of the operational logs of the services, but like all the systemd logs and all of the things we can collect from the system, so that a developer can go look through the logs and figure out, oh, that's why my patch didn't work. It's because this rabbit interaction happened inappropriately. And so that is all. It's actually one of the reasons Zuul knows next to nothing about your job output. There's a very simple, you tell Zuul at the end of a job, and the base job does this for you, but Zuul is told where your test output is, so that it can point the developer at it. It otherwise has no clue. It's just more Ansible. Whatever Ansible you need to do to collect the appropriate job output. And then in OpenStack land, we actually slam all of that output into a giant Elasticsearch cluster, so that people can do analysis on that. But some things, something that's really useful for, and some things it's not very useful for. Code linter checks, you don't really need the test job log output in Elasticsearch. It's not really very useful.
Awesome.
Yeah.
Thank you very, very much, Monty.
Thanks for having me.
I expect Monty